Hi guys, this is LA Nicole discussing Recitation 13, recursive binary search, and the Mergesort algorithm. Okay, so previously we have talked at length about binary search. Binary search implemented iteratively, right? But how exactly do we implement binary search with code, not just, have an intuition for binary search, checking middle and either looking at the lower half or the upper half of the array. How do we go from that high-level standpoint uh, to its implementation? So think back to how we would trace our binary search. What variable have we been tracking, right? We were tracking our low, we were tracking our high, and we also had our middle variable, which we were also keeping track of. And what comparison decides on how we update those variables? Right? How do we know after we compare target to the element at our middle index, how do we know whether we continue to search in the lower array or the upper array and subarray? And actually, that would be lower. And we wouldn't check middle again, right? Because after we check middle and we know that it's not our target value, we don't need to examine it again. So the comparison would be for an array sorted from least to greatest, right? If target is greater than the element at the middle index, then we would examine that upper region of the array. And if target is less than the element at the middle index, we'd examine that lower subarray. So keep in mind that that's if it's sorted from least to greatest, right? And your array does have to be sorted if you want to perform binary search on it. Otherwise, it wouldn't make sense. And if we had the array sorted from greatest to least, you would just alter that comparison, right? So like if it was greatest to least, if target was greater than the middle element, then you would examine the lower half of the array if it was greatest to least. But we in this course will we'll just stick to least to greatest. And when do we know when the search is done? Well, if we find target, if we compare the middle element to target and they are equal, right? Because we're always comparing target to that middle element as we iteratively perform binary search. If they're equal, we return index mid or index m. And that position of where we found target would be returned if we find target in the array. And if we do not find target in an array, we exhaustively perform binary search. Typically, we would return -1 to indicate that we failed to find our target in our array. So I should have said pause. So look away if you would like to try to implement binary search iteratively yourself. But this is the implementation for the iterative version of binary search. And as we can see, that those high-level characteristics that we talked about before, we're just implementing them, right? We start examining the entirety of the array from its very first element at index 0 to its very last element at index array.length -1, right? So we have our left and our right pointer. And why -1? Remember that with arrays, we start indexing from index 0, right? 0, 1, 2, 3. So even though the size of this example array is size 4, right? There's literally 1, 2, 3, 4 cells, boxes in the array. It can hold, up to 4 elements. The maximum index is 3. So the size -1, right? So that checks out. Okay, and in order to compute middle, we compute that average index of the left and the right array, indices, excuse me. Okay, so now, when do we continue to perform binary search on our array, right? When the left and the right pointers do not cross, because if they do cross, we know, oh, we fail to find our target in the array. So, right, we can update our value of middle, and yeah, if we find target, we return the index that we found it at, right? Always comparing target to the middle element, so we would return m if we found target in the array. But if not, what's the comparison? What's the comparison that we do to examine, which new region of the array we should examine? If target is less than that middle element, right? We go from examine, and if target is greater than that middle element, we'll examine from the upper portion of the array from n+1 to right or high, depending on what you named your variables. Okay, and again, why m-1 and m+1, because we don't need to examine that middle element again if we've already checked it before. So now that we did a quick review of iterative binary search, how can we implement binary search recursively, right? And with the following method signature. So if we can just jump to the hint, right? As we are no longer working with the iterative method, how do we keep track of the variables? Maybe a helper method that allows more variables in the signature, right? So you don't have to use, there's other ways you could implement recursive binary search, but because they're just restricting our parameters, they're giving us this condition to, with the following method signature, implement it. Yeah, we can use a helper method to get around that. Okay, and why is it O of log n? It's because for the worst case, for both iterative and recursive binary search, is when a target is only found, in the case of recursive binary search, at the last call of binary search, right? So we can say target found at last call, or not found at all. We failed to find the target in the array, and we had to return -1 after doing every single binary search possible, right? So the worst case is the same for both recursive and iterative binary search. And pause if you would like to practice implementing it yourself. And this is the implementation of recursive binary search, right? So it's the same concepts, except now we see in the cases where we ended a binary search, now we have them as like our base cases, right? We have our base case. If the middle element is equal to target, we return that index, that position of where we found our target. And we also have a base case of returning -1 when we have our right and left pointers cross. And if they don't cross, if right is, still greater than or equal to left, for an array sorted from least to greatest, we do our comparisons, right? And if our middle element is greater than target, we will search. We will call our binary search, or in this case, our binary search helper method on the lower half of our array, right? And the indexing remains the same as left to mid -1. And if the middle element is less than our target, then we will call our binary search helper method, or depending on how you did your implementation, just the binary search method. We will recursively call, so this is our recursive case, that binary search method on the upper half of our array. Okay, mid plus 1 to r. Okay, or high. So you could have done left right or low high, same thing. Clear? Okay. So now that we've gone over recursive binary search, let's talk about merge sort. And how does the merge sort algorithm work? So on the following slides, there will be concrete examples of tracing merge sort. On here is an array of integers and also an array of characters. And you can practice those on your own. And together, we'll go over merge sort for a general array of different sizes. Merge sort algorithm, and it is a recursive sorting algorithm. So if you're a bit rusty on recursion, go review that, and it will make learning merge sort a lot more straightforward, right? And so let's just take a look at merge sort from a very high level. Let's take a look at the code, right? So we have an array. We call merge sort on this array, right? And what the algorithm is essentially saying is we're going to sort the lower half of the array, right? We're going to sort the lower half of the array. That's what this line is saying. And we're going to sort the upper half of the array, okay? That's what this call to merge sort on the upper half of the array is saying. And we're going to recursively sort the upper and lower halves, and right, because this is the recursive case, this call to merge sort within the body of the merge sort method itself. And once we do that, we're going to call the merge method on our array, including both the lower and upper halves on our entire array. And when we merge the independently sorted lower and upper halves together, we get our completely sorted array. So say the arrays independently, the lower and upper halves independently sorted, it was 4, 6, 7, and 1, 2, 3, right? If you would just look at the lower half of the array, like as the lower subarray, you say, oh, the lower subarray is completely sorted. If you just look at the upper subarray, oh, the upper subarray is completely sorted. And so what merge does is it combines the two independently sorted halves together to create an entirely sorted array. And to see the implementation for the merge method, watch Professor Centeno's learning objective video on merge sort. Understanding the implementation for the merge method will help you understand why exactly merge sort is not an in-place sorting algorithm, unlike selection sort and insertion sort, which we were looking at before, and why merge sort actually has an O of n space complexity, because we have to use some auxiliary memory in order to perform the sorting. And merge sort is the reason why that's the case. And looking at the implementation will also make it more clear why the best and the worst case for merge sort is O of n log n. But also be able, because this is also a skill, to be able to look at merge sort from in this layer of abstraction, right? At this level, just being able to treat merge method as a black box and not feeling uncomfortable about that. So let's look at some generic arrays of different sizes. So arrays of size 1, 2, 3, and see how merge sort would apply to them recursively. And it comes back to this idea of our recursive call stack being represented by a tree to help us understand what's going on recursively. So take a screenshot of that merge sort code so you can reference it or copy it down, and we'll take a look at some cases. So let's say you had an array of size 1. And I don't know, I'll put the integer 5 in there. So we have an integer array of size 1, and we have our low and our high pointers, our references, as we can see from the implementation of merge sort that we have. And okay, they share the value 0 because low and high both refer to the index 0. So when we call merge sort to the entirety of our array, does low equal high? Yes, indeed. So we return, because by default, if we have an array of only one element, we consider that to be sorted in ascending or descending order. Whichever one you want, we consider it to be already sorted. And that makes sense, right? Because there's nothing, violating the order of least to greatest or greatest to least. You can also think of it as a degenerate case, right? It's a simpler case of being sorted to least to greatest or greatest to least. And actually, similarly, if you had an array of all the same value, so an array of all 5s, this would also be considered sorted from least to greatest or greatest to least, even though you don't usually think of this as an example of a sorted array. Right? So just want to point that out. So with an array of size 1, okay, we call merge sort on the whole array, and we go straight to the base case. Okay, so let's take a look at an array of size 2. We have an array of size 2, we have our elements 3 and 1, for example, and we have our pointers high and low, indicating the beginning and the end of the array that we're examining. So we call merge sort on the whole array. And what we're going to do is we're going to we're going to trace this code, right? Do we have an array of size 1? Does low equal high? No, right? Okay, so we calculate mid just so we have that. So I can also indicate that. Let's see, 0 plus 1 divided by 2, 0. Okay. And what we're going to do is we're going to sort the lower half of our array. We're going to call merge sort on the lower half of the array. And the lower half of the array is only one element. It's only one element, right? So for the lower half of the array, calling merge sort on this lower subarray, low does equal high. So we return, because we consider the subarray of only one element to be by default sorted, right? And then once we do that, we continue with our call to merge sort to sort the entirety of the array. And we move on to the next line to sort the upper subarray of our original array. The upper subarray of our original array. Okay, we do that call. And since it's only one element, it's by default sorted, right? Low equals high when we're examining that upper subarray. So not the values of low and high for the whole array, but the values of low and high of our upper subarray. They're equal, so we return, because an array of only one element or subarray of only one element is by default sorted. And now what we do is that we have the lower and the upper subarrays of our original array sorted, independently sorted, and then we merge them. We merge them, and what our black box merge method does is combine to make the whole array sorted. But before your exam, it should not be about black box, so make sure to watch that learning objective video. Okay, and then we're done. So we completed all the subcalls within our original merge sort call to sort our original array. And so not just the recursive calls, right? But also just, the call to merge. So we completed all the subcalls, and then we're done. So we finished the execution of the original call. So let's take a look at one more. Let's take a look at an array of size 3. So maybe this be our array. So 3, 2, 1. Okay, and low and high are our references that indicate, once again, the beginning and ending of our array. And we start again in our recursion tree, or I guess technically it's not just the recursive calls. I also put merge here just for our reference. So we have a sense of what's going on, right, as we go through the merge sort call. And so the way the tree is organized, right? Keep in mind that we have our call, and in order for our call to merge sort to finish executing, all the subcalls that are a part of that call to merge sort must finish executing first, right? And those subcalls may themselves have subcalls that also need to finish executing before their parent subcalls finish executing, right? So that's what this tree is representing. And also we do have a sense of reading from left to right that for these calls on the same level of the tree, that the ones on the left happen before the ones on the right. Okay, so with that just out of the way, we call merge sort on the entirety of the array, right? And it's not an array of size 1, so it's not by default sorted. So we go to sort the lower half of the array. We call merge sort on the lower half of the array. Reference your merge sort code that you took a screenshot of or have written down. And we call merge sort on the lower half of the array, but it's actually still not sorted by default, right? Because we have a subarray of size 2. So what we're going to do is, following the code, we're going to call merge sort again on the lower half of the lower subarray of the original array. So we call merge sort again, and the lower half of the lower subarray of the original array is 1 element, so it is by default sorted. So we finish that call to merge sort. Then we examine the upper half of the lower subarray of the original array, right? And that's also 1 element, so it is by default sorted. And once we have all of that, in mind, then we merge those two together. So if I draw our array again, once merge, that merge method finishes executing, we have 2, 3, 1. So that lower subarray is now sorted. Okay, good. So we bubble back up. We bubble back up and we're back at, our original call to sort the whole array. And we finish that subcall to sort the lower half of the array. Now let's examine the subcall to sort the upper half of the array. So we call merge sort on the upper half of our original array. And since it's only 1 element, low equals high, we return, it's already sorted. And then we merge, right? So for the next merge, so I'm gonna once again redraw our array of size 3. it becomes fully sorted because we called merged on the entirety of our original array. So I hope that gives you an intuition for merge sort, which is fundamentally just like a recursion challenge problem, which will help you do the concrete examples of the recitation problems for calling merge sort on integer arrays and arrays of characters.